Do you have to leave? Okay, we should probably get started. We have this room for an hour. I don't know if we can bust beyond the hour, but it's noon. Anyway, I'm sure everybody, maybe not on this side of the room, has seen we have juice and coffee and water and most importantly of all, cookies on this side over here. So if you want some, please go and help yourself. I'd like to welcome everyone here today for this, the inaugural lecture of the Research Talks series, which is sponsored by Ferdinand's office, the Office of the President, and also the Office of Research. And I am Bruce Muirhead. I'm an Associate VP for External Research in the Office of Research and a member of the Department of History, which I will get to in not 1 second, as well as the MC for our gathering today. I'd also like to thank, before we begin, Janet Janes and her office for putting this together. It's clearly a wonderful event. A couple of empty seats, but not very many, and we certainly had a capacity crowd sign up to come out, so I'm sure people will trickle in. So thanks a lot, Janet and Sabrina, for doing this as well. So you might think it odd, anyway, that a historian would be a front person for one of University of Waterloo's Canada Excellence Research Chairs, of course, David Corey, who will be talking about the quest for the first quantum computer. Given that I have, for example, no idea what a qubit was. I looked it up online, but not a clue what a qubit is. Still, not even so sure how to pronounce it, although I did check with them just before we began. And I don't know anything about superimposition or entanglement either, but I hope to find out today, I guess. But historians do have a role in Dr. Corey's story. We'll be writing about him in the future, the same way historians of medicine have written about Banting and Best, perhaps, and Jonas Salk, or historians of science have written about the careers of Francis Crick and James Watson as co-discoverers of the DNA molecule. Maybe the quantum computer will be David Corey's legacy to society as well. He's probing into areas that will have a massive impact upon society, and those rightfully celebrated scientists did. But first, I'll call upon Feridun Hamdullahpur, the president of the University of Waterloo, whose inspired idea this research talk series is to more appropriately introduce David Corey. You know, Feridun is an engineer wearing his other hat, so I'm sure you know a lot about quantum computing that I have not a clue about. So, with that, thank you everybody for coming out, and welcome to the first. You've set the bar very high. And we'll have subsequent ones as time passes. Just before I hand the microphone over to Feridun as well, I'll say we have another one of these coming up on March 27th, featuring Eric Kaliner from the Department of Political Science, and he'll be talking about some aspect of global financial governance, which is even less intelligible to people like me than quantum computing. So please come out for that as well. Feridun, thanks very much.
Thank you, Bruce. Thanks very much. I'm not going to take up a lot of time because we have a very exciting talk waiting for us, or we're waiting for it. But let me mention a few things. We are so lucky. We're blessed to be wherever we are. Every day something new is happening here. We are really right in the middle of this fantastic organization and time that many things are happening, and this university is making a big difference, big impact in the discovery of new knowledge and coming up with some new ideas. So when George and I were talking about this, we said, yeah, the specialists, they talk to each other, they go to conferences, they know what's going on here in these areas, but why don't we, just as this broader community here, do things that we are aware of what's going on. We don't really need to understand it to the molecular level, the subjects, but it will really enrich our presence here and our lives here if we find out what's going on. So we decided that we'll come up with this brown bag lunch series. The last time I had something from a brown bag, it was a can of beer in San Francisco. But nevertheless, the idea is a great one. So this is exactly the idea behind it. We are, as Bruce said, planning to have whole slew of topics that our community will get the opportunity to hear about, and we'll have at least a surface level idea or information about what's going on. These are the kind of things that are making us very proud, because we are really making a big difference. And I'm grateful to Professor Corey, who is the first one who volunteered, so well, I'll get it started, and then we'll have other speakers. I hope that we will continue growing this. Thank you very much for your participation, and I know that we have a lot of other people who are participating via webcast, and thank you very much again for joining us. I will stop here. Those of you who don't know David Corey, a lot of us do. He is Canada Canada Research Excellence chairholder here. We have two of them, and he occupies one of these chairs. We are very, very serious about, and we have been for a long time, to be one of the top universities in the world in the area of quantum information science. And David brings enormous amount of new knowledge and energy to this field. So I'll stop here. David, thank you very much for doing this as a volunteer and for the first time, and looking forward to your talk.
Great. Thank you very much. So I'm honored to be able to give this first one. I really appreciate that. And I noticed that I have some colleagues from IQC, from WIN, some students from my lab in the room. I'm going to tell you guys, forget every piece of physics you know. This is a different talk. Okay, so I want to tell you about building a quantum computer. I want to remind you that quantum mechanics is different than classical mechanics. And particularly, quantum mechanics is the foundation of everything we can do in the world. And so if we can build a device that is uniquely quantum mechanical, that doesn't allow any classical description, then we reach the ultimate efficiencies that nature allows us. And so there are things that we can do in the quantum world that we can't do in the classical world. We aim to build quantum computers in the lab, but we also aim to build sensors and actuators, and we'll talk about those today, but they're just as important. And in fact, the sensors and actuators are how we navigate the nanoscopic world. And at the end of the day, I could give a different talk where I would say, oh, we'll build these and then put them together in a bag, and they'll become a quantum computer. There's lots of mechanisms for building quantum devices. And I'm not going to tell you too much about the physics today. You know, you can take particles and send them in different paths. You can look at spins and diamonds and defects in diamonds. You can look at superconducting circuits. You can look at molecular circuits. There's lots of things that work. But today what we want to do is we want to get big. So, you know, we've got all of these groups working in quantum computing. And all of us have some small processor. We can do 1, 2, 3. In the group, the students back there put their mind to it. They can do 13 qubits. But that's still pretty small. What we want to do is we want to get to 100 qubits. And as I'll show you, the key thing of 100 qubits is it's big enough that it's outside of the classical world. So it's a device which we cannot even simulate with our classical resources. So we want to get to this, past this threshold of devices that we can understand by cranking through some complicated models to devices that are beyond that description. And we'll see how we're going to get there. Now I show you here just the complexity. This is a 3-qubit quantum computer that we built many years ago, last century sometime, at MIT, where we did a Fourier transform. And all of this says everything that could happen in that Fourier transform for just 3 qubits. And so I won't explain it, but lots of things can happen. Lots of things did happen. And fortunately, my students understood that. But now we're going to continue. So quantum mechanics, when I teach quantum mechanics, the very first thing I tell students is quantum mechanics is outside your everyday experiences. You know, we understand physics actually not by equations. We understand physics by telling each other stories. And, you know, that's an old idea. Go back to the historian, right? You know, sitting around fires, we're telling each other stories. And that's still how we make progress. The challenge with quantum mechanics is if you can tell a classical story, then you don't understand quantum mechanics. So you have to be careful in exactly how you can tell quantum mechanics. And the nice thing is not only that quantum mechanics is different, but that it's more powerful. And so this is an old cartoon from the New Yorker showing some aspect of a wave function if you believe that these two skis are a wave function. And of course, the piece I want you to take away from it is that this is outside of the classical world. We know what happens in the classical world, right? And how did this guy get there? He got there because the environment didn't know he went past. And that's the key. If we want to make something quantum mechanical, we have to make it so that the environment doesn't know it was there. And I want to spend a few minutes elaborating on that. And the way I'm going to elaborate on it is to think about the difference between a classical walk and a quantum walk. So if I have a classical random walk, then I could flip a coin and I could go left or right. And if I had many, many steps, then you know that eventually the probability distribution of displacement would look like a Gaussian or approximately Gaussian. And if I took more steps, it would go further, and more steps. And the distribution grows as the square root of the number of steps. Because if you're flipping a coin, it's very unlikely that it's always going to come up heads. And so you're going to be going as many times right as you go left, on average. And so we have this distribution, and we think about this distribution as having the sum over many, many paths, right? Each one of these traces could be some random path that I took. And this distribution is just the sum of over where we ended up. Quantum mechanics is different. So Cam, who's hiding somewhere in the back room, there, did the simulation for me. See, he took my quantum course, and so he knows how to do this stuff. So here we have now a random walk in the quantum version, so that at each step, the wave function goes left and right. Okay? So the wave function is spanning a result that includes left and right each time. And if I look at how this broadens, every time I increase, the wave function gets broader. And the lovely thing about this quantum random walk is that this is the probability distribution. It's not the wave function. But the probability distribution says that the most probable place you are when you do a random walk is you're at the ends. Now, you're not at the left, and you're certainly not at the right, but you are at the ends. Okay? And that is a nice result. It's a nice result that it spreads quickly, because quantum mechanically I can sample more space than I can classically. And it's nice that the wave function is a coherent superposition. I wasn't going to use the word, but since you used it, I have to. There's a coherent superposition over all these possible outcomes. And the challenge of quantum mechanics is that we cannot take this and say, oh, this is a sum over all of these different paths. Okay? I need to keep track of everything that could have happened. And so the wave function for this is huge. Whereas, of course, in the classical case, all I needed to do was to keep track of where I was. Now, this keep track of where you are, that's the key to this. If I think about, well, what's the difference between this quantum world over here and the classical world over here? In the classical world, you know, we're full of a bunch of people, busybodies, watching us and saying, oh, this guy walked that way, or he walked that way, right? And so there was some observer that knew where you were. If there's an observer who knows where you are, then that's where you are, right? Quantum mechanically, we can have a quantum state of matter provided we hide it away so that there's no observers possible. There's nothing that can tell, is he at the right or is he at the left? Okay? And if there's nothing that can tell, then the correct description is that the wave function has to be over all of it. Okay? And if I take our quantum wave function, and I just add little observers down here to say, did you see something? And we make it very unlikely that they would detect something, right? But we ask, and the stronger I make their ability to detect, the closer I get to the classical. If we kept cranking up that ability to see where the person was, we would end up directly in the classical world. So quantum mechanically, when we want to build a quantum computer, the first rule is you have to keep your quantum information hidden from all the corrupting classical environment. And everyone who's making a quantum computer, this is rule one. If I'm doing it or if Adrian's doing it back there, that's rule one. So we try to keep things hidden. Now, The next thing we have to think about is how we're actually going to engineer the system. Because we want to really build it, so we need to engineer the controls. And because the wave function has to keep track of everything, then the amount of information in it grows exponentially with the number of particles. So if I take this thing, then I could simulate about 20 qubits. So a qubit is a classical bit. You know, a classical bit, you can be up or down. A qubit is a wave function that spans up and down. Okay? So you know, if you went in and you measured the state, well, you would always find it's up or down. But the statistics of repeated measurements would be different if you have a classical and a quantum bit. So a quantum bit, I can say, oh, it's always up. That's a valid wave function. Or I can say, wow, the wave function is 90% up and 10% down. That's a valid wave function, right? And so it could be anywhere on the sphere. So my computer here can hold about 20 qubits. If I go to China and play with Milky Way 2, which is the biggest computer at the moment, this cluster corresponds to about holding the information of 35 qubits. That says if I have 35 electrons, and I can control them correctly, right? Some small issue there. I have more power than this. Now, of course, exponential is fun to look at, right? Because it just keeps getting bigger. So if I take all of the fundamental particles in the observable universe, which is under debate, it's 10 to the 80 or 10 to the 85, somewhere around there. You know, we're still looking for some dark matter. And if I asked, well, at the state of those particles in the known universe, how many qubits could we store? 250. Not many. So one of the rule 2 is keep the parts you need to model small, right? Because you're not going to model anything that's big. You know, even if they gave you the Milky Way 2, you wouldn't be able to do it. And of course, no one's going to give you the universe. Therefore, most of us that are trying to build a quantum computer are trying to build it as an array of interconnected nodes so that we have small processors that we can simulate over and we can control and we can do our engineering. And then we have quantum interconnects between them so that we have one bigger processor. Just like Milky Way 2, the computer in China. That's also a distributed computer. All right, so now let's see where we go. We need one more rule. I stole this from The Economist. So in our design, you know, 8 to 10 qubits, that's easy. It's easy for most labs. We really do know how to control them. We don't know how to get rid of errors efficiently enough. We know nothing about scales. And so as I put the rules here, and there's only 3 rules we need. You know, keep classical noise away, make an array of interconnected nodes. And this last one I'm not going to tell you a lot about. It says perform error correction in parallel. No matter how hard you try, there's always something in the environment that's going to try to figure out what your computer's state is. It could be some small magnetic particle. It could be a small vibration. It could be someone slamming the door in the hall. I tell you, we're building a new quiet labs out at the back of Rack 2, which is going to have acoustically and vibrationally really quiet space. But the noisiest thing in that building is going to be if you guys slam one of those doors. Okay? And we need to do this in parallel. You can't do it sequentially. Hilbert space is too big. You need to do things in parallel. So let's see how we're going to do this. And the basic idea that people have is we're going to have a processor with lots of nodes for us. A node is a molecule. And we're going to put them together by making a two-dimensional, one molecule thick film, the so-called Langmuir-Blodgett film. And it sounds magical, but Langmuir did it in 1920. So you can do this well. He taught us well how to do that. And so we're going to have this little molecule that we're going to use the nuclear spins and the electron spins as our processor. And eventually I'm going to stick it on top of a superconducting circuit, so we'll have superconducting electronics. And the whole thing will be cold, and it'll be in a big field. But you don't need to know that stuff. So let's start with our nuclear spins. Nuclear spins are great. They have such a tiny magnetic moment. And they're held in bonds. You know, they can't do much. They're held in place by chemistry. They have a tiny, tiny, tiny magnetic moment. And so it's hard for the environment to know that they're there. And so they keep their information for a long time. Their quantum lifetime is minutes. Okay, minutes may not sound long. But really, that's long. And they're going to be our qubits. Unfortunately, because they're so small, if I wanted to have a nuclear spin, and I wanted to connect with another nuclear spin, that's our gates, right? That's how we interact. I want to flip this one based upon that one. If you do that, the magnetic moments are so small that it takes a long time for this spin to know that this one exists. And so the gates are slow. So with an NMR, with nuclear spins, we have great lifetimes, we have lousy gate times, and the purity. So the purity says, if I want to put you in the true state, I want to put you in state spin up, how well can I do that? And you can say, well, you can almost not do it at all. And again, that's because the magnetic moment is so, so, so small. It's hard to bloody interact with those. And the last thing that's really a drag is the time it takes to reset is hours. So we got one good thing and three bad things. That's okay. Because what we do now is we say, well, okay, let's take an electron spin. Now, an electron spin has 1,000 times the magnetic moment of the nuclear spin. So it's great. We can have gate times that are fast. We can have purity 1. So all that's good. It says it's really big. And the electron spin, well, it's right there. It's an angstrom away from the nuclear spin. Or, depending on the nuclear spin, it's a femtometer away from the nuclear spin. And so it can drive the nuclear spin really quickly. If you want us to detect a small magnetic moment, you got to get up close and personal with it. And that's what the electron spin does. The quantum lifetime sucks, okay? And the reset time is still minutes, okay? But the electron spin, it has these nice pieces. So what do we do? We use the electron spin, getting ahead of myself here. There we go. We use the electron spin to control the nuclear spin. Okay, you got to remember to tell you, green's good, blue's bad. So we get the good lifetime with the nuclear spin. I get the good purity with the electron spin. Because I can control those two, they're both magnetic moments, I can take that purity and I can move it into the nuclear spin. Okay, so now then I say, good, these things don't matter because I'm going to not use the purity of the nuclear spin, I'm going to use the purity of the electron spin. And okay, so now I've gone and put one little of these dolls together. We have to keep putting those dolls together. So the next piece we do is we take the superconducting part. Because the superconducting part is a big circuit. We can cool it quickly. Just bolt it onto our refrigerator. The reset time for these electron spins was too long. But the reset time for the superconductor to reset those spins is really short. It's microseconds. And it's even better. It only happens when I push a button. I push a button, they're reset. And so on demand, fast. And so now then we have this hierarchy of systems, and we can say, yeah, rule 1 is set. Our qubits are hidden away. They're hidden away in this doll behind all of these other pieces, and we have good control. We can make a quantum computer. Now, I need to tell you how I make the nodes. I said I have these nodes. I'm just going to run over this quickly. There's an electron spin there. You see 3 bonds to a carbon, 3 bonds to a carbon. There should be 4 bonds to a carbon. There better be an electron hanging out. There's an electron hanging out. And that electron is bloody stable. These spins, we're going to treat as classical bits. What they're going to do is label the nodes of our processor. And these ones are our quantum bits. So in each node, we have 4 spins that label it and 6 spins that are the quantum processor. And so there's an array. Think about it as a tile here. I have 1 molecule. The classical bits are all indexing 0. There's 6 qubits. Here, we keep going up. Here we have the classical bits all indexed to 1, and we have 6 qubits. And the tile repeats, but that's not so important for us. What's important is that in this tile of 4 by 4, so we have 16 molecules. Each molecule has 6 qubits, so we get up to 96 qubits. So I'm sorry, if you really want to hear about 100, you have to invite me back. We only get 96. But this isn't so bad. And rule 2 is almost set. We've got a node-based system, but I haven't shown you that it's interconnected. I've shown you that we have these nodes, and we can drive them. Each one of these has an electron spin to drive it. So now I'm going to, there isn't much math, but I need a little bit of math. I'm going to teach you how to control a nuclear spin by an electron spin. And the way it does is if I look at the Hamiltonian just says, this is the energy. The energy depends upon, this says, is this electron spin up or down, the nuclear spin up or down, and these nice couplings. And if I take the nuclear spin and I point it up, so I put +1/2 here, here, and here. And then I look at what the vector is of the nuclear spin states. If the electron spin's pointed up, then there's a vector pointed out here that the spin is going to rotate about. And if it's pointed down, the vector's somewhere else. And the only way quantum mechanics works, the only thing you need to know about quantum mechanics is it's a beach ball. And if you can rotate your beach ball to any direction, then you can make a quantum computer. And so what we can do is we can say, well, if the electron spins up, I'm going to rotate about this axis. If the electron spins down, I'm going to rotate about this axis. So if I rotate for a while here, and then I rotate for a while there, I can rotate that beach ball in any direction I like, as long as those 2 aren't separated by 180 degrees. So that's all good. We have our beach ball computer. I still need one more tricky thing. I've got a nuclear spin sitting out over here. And I've got another nuclear spin sitting out over here. And I want them to connect. But remember we said the nuclear spins are wimpy. Their magnetic moment's too small. We'll never be able to detect them. But if I look at the Hamiltonian again, I find that there's an electron-nuclear interaction, and there's an electron-electron interaction. So if I have this electron and this electron, right, these are 2 different molecules. I want this nuclear spin to talk to that nuclear spin. Well, it can't do it directly, but it could do it by an interaction between this electron spin and then with this one and then this one. And this gets to be a mess. For those of you that like physics, you look at the second commutator. But for those of you that like the story, right? It said physics was a story. The way this works is you've got 1 electron spin sitting here. And you've got 2 little nuclear spins. And they're going to modulate this electron spin. But that electron spin is going to go where it wants anyways. But the nuclear spins are going to get changed. And so the electron spin can take these little nuclear spins and it can create a gate between them. And the information is transitioned between these two. But the electron spin never gets pestered. It never gets its state changed. No information ever resides on that electron spin. The electron spin is just the carrier for information. Now, I couldn't find a figure for this, but the same physics happens in parallel. If I had 20 nuclear spins, one electron spin can mediate in parallel the transfer of the information over all 20 of those spins simultaneously. And it sounds like magic, but it's not, of course. It's quantum mechanics. But the reason is that information never gets onto the electron spin. So you have these two things that don't talk to each other. They both talk to the electron spin. They send information through the electron spin from each other, but the information never is on the electron spin. And it all works. Okay, now I've got to tell you one more story. We need to cool. We need to be able to say to our quantum system, let's get everything settled down in an initial state. Initial state says, you set up your computer, you turn it on, it takes some time for it to warm up and get everything ready. The quantum computer is the same time. It takes some time, and you want all the spins to be aligned the same way. And it takes, if we were just using electron spins, well, if we were using nuclear spins, it can take forever. There's some nice stories, which I better not go into too much. But Goiter in Holland tried to do NMR first. And accidentally, he chose the wrong material. And the time it would take to come to thermal equilibrium was months. And he couldn't leave his magnet on that long. This was during World War II. Here, we want to say, okay, I'm going to take my spins. I'm going to put them in a cavity. I'm going to use this cavity to suck out the energy. So the nuclear spins they're hot there. And then they give a photon to the cavity. One of them gets cold. And then the cavity gives off the photon. And then they interact some more, and the cavity gives off another photon. And it's all good. And we can do this quickly. But the cavity is a big structure. The spins are small. So when the cavity interacts with the spins, it has to interact with them collectively. So from the point of view of the cavity, the spins need to all look exactly the same. And this is a challenging piece of physics. It's a piece of physics which has been around for a very long time, and we don't know the answer to how it works. So we start off with this hot thing. We interact with the cavity. The cavity cools the spins. But when it cools the spins, they end up in subspaces. What do we know? We know that in the subspaces, the spins are all looking exactly the same. Wake up. There we go. No, don't cheat on me. Okay, so there was some math behind that. You can forget about it. But what happens is when we cool, we enforce that the electron spins. Remember, there's no information on the electron spins. So the electron spins all get cold. They get cold really quickly, on demand. But they don't go to their ground state. They go to a state where they're all exactly the same. But one wouldn't want to describe these poor people as saying that that was the most restful state that they could be in, right? So they get into this perfectly symmetric state. And they'll be stuck there. If we only have a cavity and we cool it, we would cool quickly to these states, and we couldn't do anything more. And what we need to do is we need to break that symmetry. We need something that's going to come around and disturb them. And it doesn't need to be a big disturbance. One little nuclear spin is all it takes to disturb these guys. And then we can get at least closer to the ground state. Still not maybe so restful, but more restful than on point. And so what happens here is that, yeah, we can cool, but we still need to rewrite this rule. We actually, in fact, don't know what the answer is. And it's a nice rule in that it's beyond our ability to simulate. We'll never solve this problem on a classical computer. And I can say that, with energy, because people have tried for a long time, and there's an ongoing debate, and everyone agrees that the other guy is wrong, and all of us don't know what we're talking about. Now, we do know how to solve this. All we need to do is to take that problem and run it on a quantum computer, and then we would be golden. So one of the things that we need a quantum computer for is so that I can go and design my quantum computer on a quantum computer. And this bootstrapping, you see this in the classical world too. This is the way we make progress. We have to keep building up and building up. But it's the key step right now, because today, what we're forced to do is to do our simulations on a classical computer. And so if we're looking at simulating a handful, 2 handfuls of qubits, we can do that, but they're too small to tell us the richness of the quantum physics. And what we need to do is we need to get to our tools beyond this classical threshold. And 100 is a good place. If we can get there, there's an awful lot we can do. Now, there's a lot left to do in this program. As I just showed you, the physics of cooling and the limitations of it we need to understand. We need to understand the chemistry of such molecules and their spectra. The materials, superconductors, we're putting superconductors in a high magnetic field, and we want them to be low loss. Superconductors don't like to be in a magnetic field. Superconductors want a pairing of their electron spin like this. A magnetic field wants to pair them like this. There's some great material science that needs to be worked out. We need to be able to manufacture and control these. This, every time you see manufacturing, you think, well, that must be easy. This is hard, right? Our nanoscience, nanotechnology students, to say, take a molecular film, a film that's a millimeter by 1 molecule, and put it on there, and put it where you want. And then take it off and put the next one on. There's no way. They'll figure it out, but I don't know how to do it. And we need, of course, to have computer science control quantum information. And all of this, so if you look at my group, we span all of these activities and disciplines, and that's the advantage that we have being here. That the Institute for Quantum Computing brings together disciplines that connect us right across the university, so that we have colleagues in all the departments of engineering, math, and science, and we can share that knowledge and capabilities and bring them to bear on a common problem. So it's great fun to be here. And it's a unique environment, not only for this and the university's support, but also, of course, for Mike Lazaridis and the support that we have broadly in the community. The team of people that we have, graduate students, postdocs, undergraduates, and staff members, we would not get anywhere without the Quantum Fab. Thank you guys very much. I won't tell you about it, but there are applications. As we make this quantum computer, there's lots of spin-offs that are fun, but I'll leave that. And then this is the group at the present, or most of the group at the present, showing that the only tool they really need to do science is a coffee cup. I'll stop here. Thank you.
Thanks very much, David, for an absolutely fascinating presentation. I have to say, I do know what a Hamiltonian is, but it's probably slightly different from the Hamiltonians you were talking about. Anyway, we have 20 minutes or so, if you can hang on that long, and for a question and answer session. Anybody have any questions? I'm sure that either David or I can provide an answer. So also, if you do ask a question, we're being webcast, so I'll bring the mic around and you should speak into it. So questions? Surely there are some. Yes.
So you didn't give a lot of indication about the error rates you guys observe. Could you give some kind of an indication of the error rates you observe, kind of how you think those error rates might scale on the size of the device, and how you think those error rates are going to improve over time as the technology improves?
Yes. So thanks for the question. I mean, getting rid of errors is the most important thing. And so if we say, what's the probability that we did the right thing when we applied a gate? Well, for certain nice gates, we can get the probability to 99. For certain miserable gates, it doesn't get there, 98. How does it change with scaling? We can say, oh, I have this beautiful, simple theory that says it doesn't change at all. I'm just going to go home. But then the students will be stuck in the lab trying to do it, and they'll find that, in fact, it does change, right? And it changes because you're pushing things closer and closer together. And as you think about this, this proposal, what we're saying is we can make a tiled system of 16 nodes. And we have the control we need to do that I'm sure of. And that we can cool in parallel, and so that we can get errors out of the system in a one fell swoop. And we'll learn how to do that, right? But this isn't the way to build a commercial quantum computer. I don't know what the way is to build a commercial quantum computer. And I don't think we know enough about quantum computing to say that. The other thing that happens is up until the moment we have a quantum computer, you're forced to think of designs of a quantum computer that you can prove using classical resources. At some point, when you have a quantum computer, it's liberating. Because now, actually, you can run something and see what happens. And so one of the things that I think, as a community, we expect is that the physics and information processing is much richer than we've confined ourselves to.
I saw a hand up over here.
There's one here. David, great talk. From an engineer's mind, okay, and you said you don't quite know, what this is going to look like, but if you follow your 16-node tile, okay,
Yeah.
we're going to have a 96-qubit quantum computer. How many of these would I need if I'm able to build one? I mean, it's enough to cover the entire spectrum of classical computer capacity. Am I correct?
So
This is the first part of it.
yeah, okay.
And then fast forwarding it, this outlet in BC, they claim that they have a quantum computer. How far is it away from everything you described?
Okay.
The general audience?
Great. Okay, so let me answer both of these. If you're thinking about a 96 qubit quantum computer, it's outrageously large. For solving problems in quantum mechanics, we can solve problems in quantum mechanics that no other computer on the Earth is ever going to approach. We know that. There is no possibility that you'll ever build a classical computer that can outperform this computer for running things that are uniquely designed to run on this computer for solving quantum physics. But if you want to use it, picture your NSA and you want to break everyone's email, well, then it's nowhere near big enough. Now we need to have 1 million qubits. And there are problems where if we're trying to lead to quantum advantages by by algorithms related to computer science. We're going to need much bigger computers. And that is still a pretty open question of how we get there. For understanding material science, for understanding chemistry, for understanding engineering, these small systems will be great. For breaking encryption, we're going to need a bigger one. But I've got lots of students. They'll figure it out. Now there is, as you mentioned, there's D-Wave, who, depending upon what piece of document you look at, promises to have a quantum computer, or they're a little bit more careful. And they don't have a quantum computer. What they have is a device that does simulated annealing to look at a particular problem. The problem is one of scheduling. And scheduling is a really, really important problem to figure out where your plane should be at the end of the day, and to figure out where your trucks should be going during the day. This is really, that is a big piece of engineering. And what D-Wave has said is that they could use an annealing process to help improve that. Now, the theory of quantum computing says, the theory that we know, and we don't know everything, says that a quantum computer would not speed up that task. So it's interesting that they choose that task to develop their device. They use, of course, the word quantum computing because, it's sexy. So it gives them some attention. But they could not run the algorithms that we run here. They couldn't have done the Fourier transform that we showed, even with the 3 qubits. And they're continuing to look at the ways forward, right? I mean, in many ways, it's a great story in that they came to the field, they brought a lot of energy, and they developed some technology. They explored where it could be useful, and now they're looking for the next step. And so we'll see how those next steps play out. But I include those, our friends at D-Wave, in the pool of people that are looking to how do you build a quantum computer.
In conventional silicon technology, interconnects and packaging are becoming the limiting steps. Are you going to need a similar revolution in packaging and interconnect technology in order to actually exploit what you're building?
Yes. We don't need it yet, but absolutely. We need to have reliable quantum channels. And of course, reliable quantum channels we also need for quantum communication. So there's a reasonable number of places that will need to be able to send quantum information reliably. And if you could send quantum information back and forth, and you could do it fast, and you could do it reliably, then there are some other approaches to building a quantum computer that would look very promising. You know too much about quantum computing for this audience.
No, but I know nothing about money. My question is about money. You are receiving some money from a venture capital fund. What do you expect to get in return?
So the things that we do with Quantum Valley Investment, which has been a great partner, we don't actually talk about publicly. So that's easy. We have a startup. We're working on quantum things. And when we have a product, we'll come and tell you.
David, it was a great talk. And I'm a biologist, so I don't know much about quantum computing, if anything. And you've tried to simplify it for us very effectively by using stories. So I'd like to come back for a moment to the tree and the skier who went through the tree without the tree noticing. And then go to your other metaphor, which was the father with the 2 children in his 2 hands. And I can understand how the one child could communicate with the other child through the parent, but I'm still not quite clear how the skier gets through the tree without knowing. Because in the case of the parent is going to know what one child is signaling to him and may or may not transmit that to the second child. And the other question I have is there a finite limit to the number of nuclear spins, which in this case would be the children, that an electron spin, which would be the father, can handle? And is that a limiting feature?
Okay, thanks. So I'll answer the second one first. There's no limit to the number of kids. So if I have one electron spin, it can connect to any number of nuclear spins, but it'll take longer. And we don't know the efficiency of that. I don't know the scaling. And it's a truism of quantum mechanics that we know very, very little about efficiencies in control. In fact, the first rule you would learn if you took a control course is that the efficiency of a classical controller is a product of the power, the bandwidth, and the time. Quantum mechanically, we can exceed that. But we don't know, we don't have any recipes, and we don't know by how much. But we know we can exceed it. And the second one of the father walking with the two kids and then pushing him. Remember that the kids are communicating, but the father never knows. There's no information that ever sits with the father. And I suspect if I went and talked to kids, they would agree with me.
I cannot attest to that.
Good. And as for how do you get through the tree, we have to have some beers for that.
I have a question. That's a basic question. You're talking about cooling down the electrons. Does it mean that your supercomputer, your quantum computer, can only work inside a refrigerator?
Yes. So the question was, do we need to have our computer inside a refrigerator? And absolutely yes. And it doesn't need to be a dilution refrigerator. Now our system is a dilution refrigerator, so we're at 0.02 Kelvin. But the defining feature of having a working quantum computer is that you continually remove noise. And so that says you must be always cooling. So even if your refrigerator is working at some high temperature, even if your quantum computer is working at some high temperature, you're always going to be taking information out of it. You're going to be taking noise out of it to try to keep it as keep it on the straight and honest path.
So that really is a limitation for commercial computers.
Well, okay, that's a great question. Now, if I look at my laptop, and today you don't want to put your laptop on your lap because it gets hot, right? And the reason it gets hot is the dissipation from sending an electron. And of course, as the surface of your CPU is about as third, it has the same heat density, it's within 1/3 of the heat density of the surface of the sun. And the surface of the sun, of course, maintains its viability by radiating. We prefer our computers not radiate like that. If instead of sending information as a charge, I sent information as a spin, then I would reduce that demand by about a factor of 600. And we have the basic technology to do that today. So it's not quantum technology. It, of course, uses quantum devices. It uses quantum materials. But it uses those to do classical computing in a way that would be much, much more efficient and much faster. And one of our colleagues, Gao-Xi Miao, is trying to make those devices today. So you'll see, there's already some spintronics devices. You'll see more of that. And so my retreat is to say, we won't be pushing electrons around, so it'll be okay. You know, I worry about this word scalable. When I was first working with Lano, there was a scientist there who would say, oh yes, it's scalable. And we push him. He goes, well, it's scalable to 3. You say, well, maybe that's not scalable. And this, I have no idea how to scale it. I wouldn't want to just take that tile and make it bigger. And the reason for looking at this is really to look at the dynamics of cooling in parallel and to try to understand how we can keep errors from corrupting the system. And then to say, well, what modality will a future quantum computer use? I think it's very much like the hybrid stuff. You're going to take the best from everything you got. And so it's hard for me to imagine a quantum computer that doesn't have superconductors. It's hard for me to imagine one that doesn't have spins. Just they're a nice place to leave information hanging out. It's hard to imagine one that doesn't have photons. You need to get information here to there. You know, ions, and we're just starting to look at mechanics, right? Optomechanics is a way of connecting. So this is such a new field. It's so vibrant. And you know, we're lucky by being here. IQC has this vision of growing to 30 faculty members. We're going to have a dozen experimental groups. And at the end of the day, you know, they're going to overlap a little bit, but they're not going to sit on top of each other. And so we'll be able to cover a pretty broad spectrum. And you know, if we can work together, I think we can build that system.
We're at almost 1 o'clock. I just wanted to use MC's privilege to ask one very fast question, which may be equal parts silly and unknowable. But do you have any idea about the time frame or the time horizon for a quantum computer?
Well, you know, I've got my graduate students in the audience here, some of them. And what we say is that we can build a quantum computer in one graduate student lifetime. What we don't say is how long that is.
Well, on that happy note, thank you very much, David, for a wonderful presentation and fascinating, absolutely fascinating. Thanks. I'll tell Eric Kleiner, who is giving the next talk on the 27th of March at noon, so mark that in your calendars, that he has a very, very high bar to meet. So thanks again. Thank you.